Hello, my name's Kevin Salvage and I'm the European Regional Development Manager for LEADER based in London in the UK. And I'd like to welcome you to this short video, an introduction to SMPTE 2110 Part 10. As previously discussed in one of our earlier videos, SMPTE ST 2110 is the standard for professional media over managed IP networks. And Part 10 is the system, timing and definitions. This standard specifies the system timing model and the requirements common to all essence streams. It defines the various system clocks and the RTP timestamp creation based upon IEEE 1588-2008, SMPTE ST 2059-1 and 2, as well as AES 67. Reference documents for Part 10 include SMPTE ST 2059-1, SMPTE ST 2059-2, IEEE 1588-2019, also known as PTP version 2.1, IEFT RFC 3550 for RTP, IEFT RFC 791 for IP, and IETF RFC 768 for UDP. In serial digital interface SDI based facilities, each device is connected to a dedicated black and burst or tri-level sync reference signal, whereas in an IP network the precision timing protocol is integrated into the network connection on the device. This reference timing is critical for SMPTE ST 2110 IP video networks and is a replacement for the black and burst and tri-level sync reference system. In 2110, the video, audio and ancillary data are streamed separately, so these need to be synchronized. Inter-stream synchronization relies on RTP timestamp values in the RTP packet headers, and they are transmitted by various senders originating from a common reference clock. The common reference clock can be distributed to all participating senders and receivers via the IEEE 1588-2008 Precision Time Protocol. Synchronization across multiple essence streams at the receiving device is achieved by the comparison of the timed offsets between the RTP timestamp and the RTP clock for each of the various essence streams that share a common reference clock and its associated epoch. The transmitting side transmits the stream according to the time of the PTP. The receiving side reproduces in accordance with the time of the PTP. So let's take a more detailed look at PTP, Precision Time Protocol, or as it's also known, Standard for Precision Clock Synchronization Protocol for Network Measurement and Control Systems. Precision Time Protocol, PTP, is a protocol used to synchronize clocks throughout a computer network. In 2008, IEEE 1588 was released as a revised standard, also known as PTP version 2. It improves accuracy, precision and robustness, but is not backward compatible with the original version. IEEE 1588 is designed to fill a niche not well served by either of the two dominant protocols, NTP and GPS. IEEE 1588 is designed for local systems requiring accuracies beyond those attainable using NTP. It is also designed for applications that cannot bear the cost of GPS receivers at each node, or where the GPS signal is inaccessible. SMPTE 2059 describes how to synchronize video equipment over an IP network. A profile is a parameter that is optimized for a specific industry type or a specific purpose, and the SMPTE profile has been optimized for broadcast networks. Uniquely determine video and audio phase at arbitrary time. So let's take a more detailed look at the PTP specification and video phase. Both the IEEE 1588 and SMPTE epoch are the same, namely the 1st of January 1970 at a time of 0 hours, 0 minutes, 0 seconds, based upon the International Atomic Time. The profile objective is that synchronization should be established within 5 seconds. The synchronization between any two followers is synchronized with the leader with an accuracy of within 1 microsecond to send synchronization metadata. Transport specification supports both IP version 4 or IP version 6 with multicast, mixed mode or unicast. Multicast transmissions of PTP is transmitted with a multicast address of 224.0.1.129. So with the PTP epoch of the 1st of January 1970 at 0 hours, 0 minutes and 0 seconds, this allows us to calculate the video phase at the arbitrary time of t. So let's take a look at the terms and definitions around system timing. To start with, we have the Grand Master Clock, the ultimate source of time for clock synchronization using PTP. Next we have the Leader Clock, formerly known as Master Clock, a clock that is the source of time to which all other clocks on that path are synchronized. Next we have the Follower Clock, formerly known as a Slave Clock, and this is a clock that synchronizes to another clock. Next we have the Boundary Clock. Every port acts as a PTP node, or ordinary clock. Time is regenerated and forwarded to all followers, and this is suitable for SMPTE ST 2110 infrastructures. Next we have the Transparent Clocks. Resident time is measured for every PTP packet. Timestamps are drawn at ingress and egress. Differences is added to the correction field, and this is suitable for small scale systems. Next we have the Best Master Clock Algorithm, or BMCA, that allows automatic selection of the Grand Master. And finally we have PTP domain, a logical grouping of clocks that synchronize to each other using PTP, but may not be synchronized to other clocks in another domain. So how do we calculate the timing parameters of a PTP network? One method is what's known as the one-step mode, where a series of messages are sent between the PTP leader and PTP follower. This starts with the leader sending a sync message, including the master transmission timestamp T1 to the follower. The follower receives the sync message and records the received follower timestamp T2 and the leader transmission timestamp T1. The follower sends a delay request message to the leader and records the follower timestamp T3. The leader receives the delay request message and records the received leader timestamp T4. The leader includes the timestamp T4 in the delay response message and sends the timestamp T4 to the follower. With this, the follower possesses all 4 timestamps, and by using the 4 timestamps we can calculate the average network path delay of a message between the leader and the follower. We can also calculate the offset of the follower clock from the leader. Ideally, the offset calculation is based upon the assumption that the time the message is transmitted from the leader to the follower and the time transmitted from the follower to the leader are the same. However, in reality, asymmetric packet delay time can also occur due to the length of the time the packet stays in the switch or the network routing changes. So the average transmission time fluctuates. The sync message is sent 8 times or more per second. The second method is known as the 2-step model, and this is very similar to the first 1-step model, the difference being that the leader sends a follow-up message after the sync message. So what are the pros and cons of the one-step or two-step mode? The advantages of one-step are as follows. One step is simpler at the follower end, as it must only receive one message, whereas with two-step the follower clock must receive two messages before it can set its own time. The main advantage of this is that it guarantees that each sync message is correctly linked up with its timestamp, especially when there are many multiple possible network routes. Two-step, on the other hand, theoretically risks timing packets getting mixed up, which rules it out of end-to-end PTP networks. This is especially true on networks with redundancy protocols such as Parallel Redundant Protocol, PRP, and High Availability Seamless Redundancy, HRS, in which there's more than one way a packet can travel to its destination, and therefore more than one length in time it could take to get there, meaning the order of the receipt could be wrong. This can be alleviated by using packet sequence numbers to match things up correctly at the follower end. However, this adds complexity. The advantages of two-step. At the sending or leader end, it's easier to go with two-step due to the processing work involved in appending the required information to a one-step sync message. Two-step doesn't need to write timestamps to messages as they leave, which can make two-step leader clocks cheaper up front in terms of hardware. This also increases flexibility. Changes can be made to the way packets are coded without changing hardware. It's even better when it comes to future-proofing. The more relaxed hardware needs means that in future there's less chance of needing new hardware to handle updated standards or protocols. This is related to how it's easier to modify the formatting of packets. Two-step is also the only option if using a 10 gigabit or higher Ethernet link, due to the limited time to encode messages at higher bit rates. The simplicity of two-step makes this a non-issue. Again, this helps future-proof. So let's take a look at the network path delay measurement. As previously mentioned, in reality, asymmetric packet delay time can also occur due to the length of time the packet stays in the switch or the network routing changes. So the average transmission time can fluctuate, as can be seen from the delay time graph on the screen, which displays the current maximum as 2.43 microseconds and the current minimum as 1.784 microseconds. So let's now take a look at the time offset graph. As previously mentioned, ideally the offset calculation is based on the assumption that the time the message is transmitted from the leader to the follower and the time transmitted from the follower to the leader are the same. The timed offset graph shows the max, min and current time offset. So now let's take a look at the best master clock algorithm. A key to the resilience of the PTP network is the best master clock algorithm. The BCMA allows a clock to automatically take over the duties of a grandmaster when the previous grandmaster loses its GPS, gets disconnected due to a switch fault, or for whatever reason is unable to continue as a grandmaster. So let's take a more detailed look at the best master clock algorithm. The BMCA is an algorithm that selects the grandmaster with the highest quality from the leaders on the network. The leaders exchange clock information with each other and decide the grandmaster. The clock information is as follows, and it compares in order from the top. Starting with priority 1, a value indicating the superiority of the leader is given priority over the smaller one. Optional settings by the user are possible. Next we have clock class, clock accuracy and clock variance. These values represent the quality of the clock. inside the device and the external reference that it's connected to. Finally, we have priority 2, and once again, like priority 1, this value can be adjusted by the user. So let's take a look at an example of the best master clock algorithm. PTP leader 1 sends information that priority 1 is set to 0 on this network. PTP leader 2, which has priority 1 set to 1, receives leader 1's priority 1 data and is informed that it is set to 0. Since priority 1 of a PTP leader 2 is set to 1, it therefore has a lower priority than the PTP from leader 1, resulting in the leader function of this PTP generator being set to standby. So let's take a look at the best master clock algorithm running in real time. And as previously mentioned, you can see the various parameters from domain number, original timestamp, priority 1, and the various clock classes through to priority 2 and the time source. We're monitoring both ports 1 and port 2 in this example. So now let's take a look at PTP domains. Every PTP message contains a domain number. A PTP instance is configured to work in one and only one domain. It is required to ignore messages from any other domain number. The point of this complication is to allow different independent timing systems to inhabit the same network without confusing each other whilst using one physical Ethernet connection. In the example being displayed, the system is configured with the domain divided. Some audio equipment only supports the profile of AES67. So now let's take a look at IEEE 1588-2019, also known as PTP version 2.1. Backwards compatibility with previous standards is vital. The working group should ensure that the resulting draft has the highest degree of backwards compatibility possible with the previous editions of IEEE 1588. So what does backwards compatibility mean? New edition devices will not break the 2008 edition network, meaning you can take a PTP version 2.1 device and put it into a PTP version 2 network and vice versa. New features are optional, and old features will work as before. So let's take a look at some of the new features included in IEEE 1588 PTP version 2.1. So first we have multi-master PTP. A robust clock aggregates the timing obtained from 3 PTP instances in order to identify a faulty time source. Hybrid operation. The announced message is multicast to all follower clocks. A sync message is multicast to all follower clocks, sending the T1 timestamp. Followers now have both T1 and T2 timestamps. Follow-up message is sent only if you're using two-step mode. The follow-up message is used to send the correct time of the sync message. The delay request message is a multicast message from the follower clock to the grandmaster. Since it's multicast, it goes to every device that is listening to the PTP. So all of the other follower clocks receive this message. Delay response message. The grandmaster sends a T4 timestamp to the follower clock that sent the delay request message. But it's a multicast message, so every follower clock receives that message. So as you can see, this results on the extra load on the switch. So let's take a look at mixed mode operation. An announce message is multicast to all follower clocks. A sync message is multicast to all follower clocks. This sends the T1 time to the follower. So now it has both T1 and T2 timestamp information. Follow-up message is sent only if you're using two-step mode. The follow-up message is used to send the correct time of the sync message. The delay request message is a unicast message featuring the T3 timestamp from the follower clock to the grandmaster. Since it is unicast, no one else gets that message except for the grandmaster. Delay response message. The grandmaster sends T4 timestamp to the follower clock that sent the delay request. This is a unicast message, so only the follower clock that sent the delay request gets the message. So as you can see, the load on the network switch is now a lot less. So thank you for joining us for this introductory session to SMPTE 2110 Part 10, System Timing and Definitions. And if you have any questions, please don't hesitate to contact me on the numbers currently displayed on the screen.